Cherry Coca-Cola, Pepsi, and Fanta Grape all hide their secrets inside the syrup. One twists an iconic cola with a sharp cherry note, one balances a darker classic formula, and one turns grape flavor into a secretly produced soda. In this video, we uncover how these drinks are blended and carbonated before their flavors travel the entire world. Cherry Coca-Cola production begins when a cherry flavor stream is metered into a dark cola syrup base. The cherry component is powerful, so it enters through a controlled dosing line rather than as a large volume. A metering pump pushes it into a stainless steel tank where the cola syrup is already circulating. The agitator pulls the liquid inward, drives it downward, and folds the cherry stream through the dense syrup until the added flavor no longer exists as a separate layer. The cola syrup itself has been built before this point. Treated water enters a syrup tank first. It is not ordinary, untreated water. It has already moved through filtration systems that remove suspended particles, activated carbon beds that reduce unwanted taste and odor, and polishing stages that stabilize clarity and mineral profile. A measured volume of this treated water is held inside the syrup vessel. Sweetener is added through a dosing system. In some plants, the sweetener enters as granulated sugar. In others, a liquid sweetener stream is used. The agitator keeps the water moving so the sweetener disperses quickly. If dry sugar is used, the crystals fall into the moving water and dissolve gradually. The liquid becomes heavier and glossier as the sugar disappears. Mild heat may help the dissolution process, but the syrup is not boiled. The purpose is to create a smooth, sweet base with no grit or undissolved particles. The sweet base passes through fine filtration. This removes any remaining solid material before flavor concentrate is added. Clean syrup protects the pumps, meters, proportioning valves, and filling heads later in the line. Cola concentrate then enters through a closed pipe. It brings the core cola flavor, caramel color, acidity structure, and formula components that define the base beverage. The syrup darkens almost instantly. The tank changes from a clear sweet solution into a deep brown concentrate. The agitator continues turning. Dark streaks vanish into the syrup. The mixture becomes uniform from the top surface to the outlet at the bottom of the tank. This syrup is still too strong to drink. It is a concentrated flavor and sweetener base designed for precise dilution later. The cherry flavor addition is integrated into this cola syrup system. It must not overpower the cola base or remain uneven in the batch. The mixing sequence creates a combined cola cherry syrup that carries both profiles in one concentrated stream. The finished syrup moves into a holding tank. The tank may use slow agitation to keep the syrup uniform. Sensors monitor level and temperature. From here, a sanitary pump sends syrup toward the proportioning system. A separate treated water stream leaves the storage tanks and travels toward the same proportioning unit. This water bypasses the syrup tank and remains clear until it reaches the blender. Both syrup and water pass through flow meters. The proportioner is the point where concentrated syrup becomes finished strength cherry Coca-Cola. One line carries the dark cola cherry syrup. The other carries treated water. Automatic valves make continuous adjustments so the blend ratio stays fixed, even if pressure changes inside either line. Inside the mixing chamber, the syrup and water combine. The syrup thins rapidly. The color remains deep, but the viscosity drops. The beverage now has its finished sweetness, acidity, cola flavor, cherry note, and caramel brown appearance. It is still flat. The flat drink moves through a chilling system. It passes through a plate heat exchanger made from thin stainless steel plates. A cold circulating medium flows on the other side of the plates and draws heat away from the beverage. The liquid temperature drops quickly while the product remains sealed inside the system. cold liquid absorbs carbon dioxide more efficiently than warm liquid. It also foams less during filling. This matters because a carbonated cola must enter cans or bottles at high speed without overflowing or losing too much gas. The beverage may pass through a deaeration stage before carbonation. In a deaerator, reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing unwanted air helps the drink accept carbon dioxide more cleanly. Carbon dioxide enters through regulated gas lines. The gas is filtered and pressure controlled before reaching the carbonator. Inside the carbonator, chilled cherry Coca-Cola meets carbon dioxide under pressure. The gas dissolves into the liquid rather than escaping as bubbles. The drink now has its sparkling bite. From this point onward, it stays inside closed pressurized stainless steel pipework. A sudden pressure drop would release foam and reduce carbonation, so the finished beverage flows directly toward the filling machine. While the liquid is prepared, containers move along their own factory path. For PET bottles, the process begins with preforms. A preform is a short, thick plastic tube with a finished neck. The threads, sealing surface, and tamper band support are already molded. The body still has to be stretched into a full bottle. Preforms enter a heating oven. Infrared lamps warm the plastic body while each preform rotates. Rotation keeps the heat even around the circumference. The neck area is kept cooler so the threads do not distort. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes downward through the center, pulling the softened plastic lengthwise. Compressed air then expands the plastic outward until it touches the chilled mold wall. The bottle shape appears instantly. The base forms into pressure-supporting feet. The shoulders and label panel set into the plastic. The mold opens and the new bottle exits by its neck ring. The bottles move through air conveyors. They are light before filling, so streams of air push them forward while rails support them by the neck. They travel toward rinsing in single-file rows. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. It drains briefly, turns upright again, and moves toward the filler. Aluminum cans follow another route. They arrive already formed and printed, open at the top. The cans enter an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottles arrive fully formed. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and inside surface. Defective bottles are removed before they can reach the beverage. The carbonated cherry Coca-Cola reaches the rotary filler under pressure. The filler contains many valves arranged around a circular carousel. Containers enter through a star wheel that spaces them evenly beneath those valves. A bottle seals against its filling valve. Pressure inside the bottle is balanced with the filler before liquid enters. This prevents the carbonated drink from surging into foam. For cans, the filling system also controls flow carefully to limit turbulence. The valve opens. Dark sparkling cherry Coca-Cola flows into the container in a smooth stream. In a clear bottle, the liquid rises from the base, carrying fine bubbles through the brown body of the drink. The fill level reaches the programmed height and the valve closes. The filled container moves immediately toward closure. Plastic bottles pass under capping heads. Caps are fed from a bulk hopper, sorted into the correct orientation, and delivered down a chute. Each capping head places a cap on the bottleneck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed on each filled can. The can and lid rotate together, while seaming rolls fold the lid curl and can flange into a tight double seam. The seal traps carbonation inside without glue. Glass bottles receive crown caps. A metal crown is positioned over the mouth and pressed down. The ridged skirt crimps under the glass bead, forming a gas-tight closure. Sealed containers move directly through inspection. Fill level sensors check the amount of liquid. Cameras inspect cap angle, tamper band position, lid seam, crown placement, bottle shape, and printed surfaces. Any container outside tolerance is rejected by an air jet or mechanical pusher. Bottles then move toward labeling. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the printed marks. A cutter separates each label, adhesive attaches the leading edge, and the bottle rotates as the film wraps around the body. The trailing edge is secured with another adhesive point. Rollers smooth the label around the bottle so it sits straight and tight. Cherry Coca-Cola labels identify the variant, while the liquid inside remains the same dark cola color. Shrink sleeve labels may use a different route. A printed sleeve drops loosely around the bottle. Heat then shrinks the sleeve tightly to the container contours. Glass bottles can receive glued paper labels pressed flat by brushes as the bottle turns. Cans usually carry their printed design before filling, so they move from seaming and inspection directly toward coating and packing. Pepsi production is astonishing. The liquid entering the first stage is already sweetened, flavored, colored, acidified, filtered, and blended to finish strength. It is cold enough to hold gas efficiently. The carbonator keeps it under pressure while carbon dioxide enters through diffusers or contact surfaces. The gas breaks into fine bubbles, dissolves into the cola, and gives the drink its sharp, sparkling structure. Inside the sealed vessel, pressure is controlled constantly. If the pressure drops too suddenly, the dissolved gas would escape as foam. If the temperature rises, the liquid would hold less carbon dioxide. The system balances liquid flow, gas pressure, and temperature so every liter leaves with the same carbonation level. The carbonated Pepsi moves through closed stainless steel pipes toward the filler. The line stays pressurized. Bends are smooth. Valves open gradually. Every part of the route is designed to keep the liquid calm because turbulence can knock gas out of solution before the package is sealed. The rotary filler is already moving as the drink arrives. Empty containers enter one by one through star wheels that space them evenly. Each container rises or is lifted into contact with a filling valve. The valve seals around the mouth before the beverage flows. For bottles, the filler first balances pressure inside the empty bottle with the pressure inside the beverage bowl. This prevents the cola from flashing into foam when the valve opens. Once pressure is equalized, Pepsi flows down the filling tube and climbs up the container wall in a dark, glossy column. The fill height is controlled precisely. Too little liquid creates an underfilled package. Too much liquid leaves insufficient headspace and can interfere with closure. When the level reaches the programmed point, the valve closes, and the filled bottle moves immediately to capping. For cans, the same goal is achieved with high-speed fill valves that reduce splashing and foam. The can receives the carbonated cola quickly, but the stream is shaped to keep the surface controlled. The can exits the filler with a small open headspace, ready for seaming. Long before this filling stage, the water has already been prepared. Incoming water passes through a treatment system. It moves through filters that remove suspended material. Activated carbon reduces unwanted odor and taste. Additional polishing steps stabilize the mineral profile and clarity. The finished treated water becomes the base for both syrup production and final dilution. Part of the treated water enters the syrup room. This area produces the concentrated Pepsi syrup. Sweetener is added first. Depending on the plant and product format, this can be liquid sweetener or dissolved sugar. The sweetener enters a stainless steel tank where an agitator keeps the water moving. When sugar is dissolved, the liquid becomes heavier and more reflective. The mixing system keeps crystals from collecting on the bottom. The syrup is circulated until it is smooth and free of undissolved particles. It then passes through filtration before flavor concentrate is added. The flavor concentrate enters through a sealed dosing line. It is added in a much smaller volume than the sweetener base, but it defines the cola profile. The liquid in the tank darkens as caramel color spreads through the batch. Acids, flavor components, and cola ingredients blend into the sweet base. The agitator turns steadily, not violently. The syrup must become uniform without drawing air into the liquid. Air pockets can interfere with pumps and later carbonation. Once mixed, the syrup has a deep color, strong flavor, and much higher concentration than the final drink. The syrup is held in a dedicated tank. From there, it is pumped to a proportioning system. The proportioner combines syrup with treateds, water at the exact ratio needed for finished Pepsi. Flow meters measure both streams. Automatic valves make small corrections while the system runs. The syrup stream is dark and dense. The treated water stream is clear and light. They meet in a blending chamber and become one continuous cola stream. The color remains deep brown, but the sweetness and acidity now match the finished beverage. At this point, the Pepsi is flat and uncarbonated. The blended cola passes through a chilling unit. Thin stainless steel plates separate the beverage from a cold circulating medium. Heat transfers out rapidly. The liquid temperature drops, preparing it for carbonation. Cold cola foams less, fills more cleanly, and holds dissolved gas more effectively. Some systems remove dissolved air before carbon dioxide is added. In a deaeration unit, the beverage moves under reduced pressure or through a controlled contact system. Air separates from the liquid and is removed. This gives carbon dioxide more room to dissolve and helps keep the final taste consistent. The chilled, deaerated cola then enters the carbonator, where carbon dioxide is absorbed under pressure. From there, the drink moves directly into filling and closure. Bottle production can happen on the same site or before the bottles arrive at the plant. PET bottles often begin as preforms. A preform is a small, thick plastic tube with a finished neck and threads. Only the body remains unformed. Preforms enter a heating tunnel. Infrared lamps warm the plastic body, while each preform rotates. The heat must penetrate evenly. The neck finish stays cooler because it already has its final shape and must not distort. The heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, elongating the softened plastic. Then, compressed air expands it outward until it presses against the mold walls. The bottle shape appears in a fraction of a second. The base forms pressure-resistant feet. The label panel forms along the sidewall. The shoulders and body cool against the mold surface. The mold opens, and the finished empty bottle exits by the neck ring. The bottles travel on air conveyors. They are so light that directed air can push them forward, while rails support their necks. The bottles move toward rinsing, filling, capping, labeling, and packing without being squeezed by heavy belts. Aluminum cans arrive open at the top. They are already shaped and usually already printed. The can body is thin, light, and designed to receive an aluminum end after filling. Before filling, cans pass through rinsing equipment. They invert, receive filtered air or water, drain, and return upright. Glass bottles move through inspection before filling. Light and camera systems check the mouth, base, sidewall, and interior. Any bottle with chips, cracks, contamination, or shape defects is removed before reaching the filler. After carbonated Pepsi is filled, closure happens immediately. Plastic bottles pass under rotating capping heads. Caps feed from a hopper into a sorting system that turns them into the correct orientation. Each cap drops onto a bottle neck. The capping head tightens it to a controlled torque. The tamper band locks below the neck ring. Cans enter a seamer. An aluminum lid is placed onto the filled can. the can spins, while seaming rolls fold the lid curl and can flange together. The metal folds into a tight double seam. This seam traps pressure without adhesive. Glass bottles receive crown caps or other closures, depending on the format. A crown cap is placed over the mouth and pressed downward. The skirt crimps under the glass bead, forming a gas-tight seal. The sealed containers move through inspection. Fill level sensors check the liquid height. Cameras examine caps, seams, crowns, tamper bands, dents, label panels, and container alignment. A defective bottle or can is pushed off the conveyor automatically. Bottles then continue to labeling. If roll-fed labels are used, printed film unwinds from a large roll. Registration sensors read timing marks. A cutter separates each label. Adhesive attaches one edge to the bottle, and the bottle spins as the label wraps around its body. The trailing edge receives adhesive and presses flat against the first edge. Rollers smooth the film so the label sits tight without wrinkles. The blue Pepsi branding is applied as part of this printed label or already present on printed can bodies. Fanta, grape syrup, is much stronger than the drink in the bottle. It carries sweetener, acid, grape flavor, color, and stabilizing ingredients in concentrated form. As it enters the blending chamber, flow meters measure every movement. The treated water line moves beside it. Control valves adjust both streams, so the finished beverage holds the same ratio from the first container to the last. Inside the blender, the purple syrup thins instantly. The liquid changes from dense concentrate into bright grape soda base. Its color remains strong, but the texture becomes lighter. The blend is not sparkling yet. It is flat, chilled, and ready for carbonation. Before the syrup reaches this point, it is built in the syrup room. Treated water is pumped into a stainless steel tank. The tank has a polished interior, a bottom outlet, and an agitator that turns at a controlled speed. Sweetener enters first. Granulated sugar may be dissolved into the water, or liquid sweetener may be metered directly into the tank. If sugar is used, the crystals fall into the moving water and disappear gradually. The liquid becomes heavier and clearer as the crystals dissolve. A recirculation pump can pull syrup from the bottom and return it near the top, helping the batch become uniform without leaving dense sweet spots inside the vessel. The sweetened base passes through fine filtration. This catches undissolved material before flavoring and color are added. A clean syrup is easier to pump, easier to meter, and less likely to disturb the filling system later. The grape flavor concentrate enters through a closed dosing line. It is not added by volume guesswork. It is pumped in at a measured rate. The agitator pulls the flavor into the sweet base, and the tank slowly changes character as the grape profile spreads through the syrup. The purple color system is added in the same controlled way. A small amount changes the entire tank. Dark ribbons appear briefly around the inlet before the mixer folds them into the batch. The syrup shifts into a uniform purple tone with no streaks or pale zones. Acid ingredients are dosed into the syrup to sharpen the fruit profile and balance the sweetness. They dissolve into the moving liquid and change the sensory structure of the drink, but the process remains mechanical. Tank, pump, meter, agitator, sample point, and transfer line. The finished Fanta grape syrup rests in a holding vessel. Slow agitation keeps it consistent. Temperature is controlled, so viscosity stays predictable. A pump then sends it toward the proportioning skid, where it will be diluted into finished beverage. The clear water used for dilution has its own route through the plant. Incoming water passes through particulate filtration first. This removes suspended solids that could affect clarity or damage equipment. It then moves through activated carbon, where unwanted taste and odor compounds are reduced. Additional polishing stages may adjust the mineral balance and remove fine impurities. The treated water must be consistent because it forms most of the finished drink. Even a small change in water profile can affect flavor, carbonation behavior, and appearance. After treatment, the water flows into storage tanks. These tanks keep the water ready for syrup making and final blending. Level sensors monitor the supply. Pumps draw from the tanks as the production line demands more volume. From the proportioning skid, the flat Fanta Grape beverage moves toward chilling. A plate heat exchanger lowers the temperature quickly. The liquid flows between thin stainless steel plates while a cold medium flows on the opposite side. Heat transfers through the metal and the drink leaves colder than it entered. Cold soda accepts carbon dioxide more efficiently than warm soda. It also foams less during filling. This matters because Fanta Grape must hold carbonation while moving through pipes, valves, and containers at high speed. The chilled liquid may pass through a deaeration step. In this unit, unwanted dissolved air is pulled from the beverage. Reduced pressure or controlled gas contact helps tiny air bubbles leave the liquid. Removing air makes carbonation more precise and helps the grape drink retain a cleaner sparkle. The flat, chilled beverage enters the carbonator. Carbon dioxide flows in under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the liquid. The drink changes from still purple, soda base into carbonated Fanta Grape. From this point, the beverage stays inside closed, pressurized stainless steel pipework. Sudden pressure loss would release foam, so the route to the filler is smooth, short, and carefully controlled. The purple liquid moves forward without open tanks or splashing. Containers are prepared at the same time. PET bottles often begin as preforms. A preform is a thick plastic tube with the neck already finished. Threads and the sealing surface are complete, but the body is still small and heavy. The preforms enter a heating oven and rotate as infrared lamps warm the plastic. Once heated, each preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, while compressed air expands the softened plastic outward. The bottle body forms against the cold mold walls. The base, shoulders, label panel, and sidewalls appear in one fast expansion. The mold opens, and the empty bottle exits by its neck ring. Air conveyors move it forward. Because the bottle is light before filling, it can be carried by its neck while air jets push it along the rails. Cans follow a different path. Empty aluminum cans arrive already shaped and usually already printed. They are open at the top. Before filling, they pass through a rinser that inverts them, blows filtered air inside, and returns them upright. Glass bottles move through inspection before filling. Cameras and light beams check the mouth, base, sidewall, and interior. Any damaged or contaminated bottle is rejected before it reaches the drink. The carbonated Fanta Grape enters the rotary filler. The filler contains many valves arranged around a circular bowl. Bottles or cans move into position through star wheels, each one timed to match a filling valve. For plastic bottles, the container seals against the valve. Pressure equalizes before liquid enters. This prevents the soda from foaming violently. Once balanced, the valve opens and purple carbonated soda flows into the bottle. Fine bubbles rise through the liquid as the level climbs. The valve closes at the programmed fill height. The headspace above the liquid is kept within a set range. The bottle leaves the filler and moves immediately to capping. Caps are fed from a hopper into an orienting bowl. Each cap turns into the correct position and travels down a chute toward the capping heads. The head places the cap onto the bottle and tightens it to a controlled torque. The tamper band locks below the neck ring. For cans, the filled container moves into a seamer. An aluminum lid is placed over the open top. The can and lid rotate together while seaming rolls fold the lid curl and can flange into a double seam. The seal traps the carbonation inside the can. The The process for Sprite begins with the transformation of municipal water into beverage-grade base water. This water enters through insulated pipelines and is immediately routed into a sequence of stainless steel treatment vessels. First, it flows through a coarse mechanical screen to eliminate large particles. It then enters a pressurized sand filtration unit filled with graded quartz media, where finer solids are trapped. After this, the water moves into an activated carbon filtration chamber. Here, as it passes through beds of carbon granules, residual chlorine, organic molecules, and off odors are removed through adsorption. Next, the water is softened in a dual-tank ion exchange system. Calcium and magnesium ions are replaced with sodium ions to prevent mineral buildup in downstream equipment. From there, it proceeds into a reverse osmosis module, which uses pressure-driven membrane filtration to remove dissolved salts, nitrates, and bacteria. The output is ultra-clean water with consistent properties. Before storage, it is exposed to ultraviolet irradiation and passed through a 0.2 micron sterile filter to eliminate any remaining microbes. The treated water is directed into large, sealed stainless steel tanks fitted with slow-turning paddles that keep the fluid agitated and uniform in composition. Meanwhile, the flavor syrup is prepared in a separate, climate-controlled mixing room. The process begins by transferring liquid sweeteners, either high fructose corn syrup or refined liquid sucrose, from bulk storage tanks into jacketed blending vessels. These vessels are equipped with load cells to ensure exact quantities are used. Agitators start spinning to ensure even distribution. Into these vessels, concentrated flavor ingredients are injected using computer-controlled microdosing pumps. These include lemon lime oil emulsions, natural citrus flavor distillates, and bitterness balancers. Citric acid is added as the key acidulant to provide Sprite's distinct tart profile. Sodium citrate is introduced to regulate the beverage's buffering capacity and stabilize acidity. Small quantities of preservatives are introduced last. The mixture is kept under continuous motion with variable speed impellers that prevent stratification. Once all components are incorporated, the syrup is heated rapidly in a tubular heat exchanger, held at pasteurization temperature for a brief duration, and then chilled through a countercurrent cooling system. Once cooled, the syrup is passed through a sterile filter and stored in closed-loop storage tanks under positive nitrogen pressure to prevent contamination. The next phase is inline blending. In this stage, the finished syrup is metered into a continuous stream of purified water. The blending takes place inside a high-precision mixing manifold, where magnetic flow meters monitor the real-time ratio of syrup to water. Proportional integral derivative controllers adjust valve positions automatically to maintain a consistent blend ratio. Inline refractometers provide Brix readings that validate sugar concentration. Once the beverage stream is formed, it moves into a deaeration tank where vacuum pumps lower the internal pressure to remove dissolved oxygen. This step is critical to improve carbonation absorption and prolong product stability. The deaerated mixture then flows into a cooling module that chills the liquid to near 0 graus Celsius using a glycol-based refrigeration loop. Lowering the temperature increases the solubility of carbon dioxide in the next step. Carbonation takes place in a pressurized tank equipped with high-efficiency diffusers. Liquid CO2 is injected under controlled pressure through stainless steel sparges that break the gas into fine microbubbles. As these bubbles rise through the cold beverage, the carbon dioxide dissolves into the liquid under saturation pressure. A circulation pump ensures the beverage continuously cycles through the carbonation chamber for uniform gas distribution. Inline gas volume analyzers measure the carbonation level in real time, while PID loops adjust CO2 flow rate and internal pressure accordingly. The carbonated product exits into a buffer tank held under constant pressure, ready for filling. Container preparation is a continuous process occurring in parallel. PET bottles or aluminum cans arrive from high-speed depalletizers that remove layers of empty containers using suction pads and robotic arms. The containers are placed onto conveyor belts and directed toward the rinsing system. For bottles, an inverted air rinse machine uses ionized air jets to dislodge any debris inside. Cans are washed with sterile water sprays and dried with compressed air. Once cleaned, the containers proceed toward the rotary filler. Filling occurs on a multi-head rotary machine where containers are positioned under filling valves arranged in a circular turret. The carbonated beverage is delivered from the pressurized buffer tank to the filler bowl. Each container is raised into position and sealed against a filling nozzle. First, the internal pressure of the container is equalized using a pre-evacuation chamber. Then, the valve opens and liquid flows in under gravity or slight overpressure. Vent tubes allow displaced gas to escape without disrupting carbonation. Once the container reaches its calibrated fill height, the valve closes and the container is lowered back onto the conveyor. Capping follows immediately. For bottles, caps are sorted and oriented using centrifugal feeders and fed into a rotary capper. Each cap is pressed onto the bottle and secured using torque-regulated chucks. Sensors verify cap presence and alignment. For cans, ends are placed on top by an end-feeding chute, and a seaming head curls the lid over the rim in a multi-stage process to form a hermetic seal. Once sealed, the containers pass through a pressurized water spray or vacuum chamber to remove any residual product from the exterior. The sealed containers move toward quality assurance. Systems. High-speed cameras check for correct fill levels, proper capping, and label placement. Infrared sensors detect internal pressure by analyzing surface deformation. Some containers are automatically diverted for destructive testing, including carbonation loss, torque verification, and microbiological sampling. Labeling varies by container type. For PET bottles, self-adhesive labels are applied using servo-driven applicators that wrap labels around the cylindrical surface. The applicator head synchronizes with container speed and uses rubberized rollers to press the label into place. In canning lines, shrink sleeves are applied over the containers, and the cans pass through a steam or infrared tunnel that contracts the film tightly around the can body. Optical sensors verify label presence, orientation, and print clarity. Labeled containers are grouped into multi-unit packages by a high-speed collation system. Bottles are mechanically pushed into plastic carriers or enclosed in cardboard sleeves using servo arms. Cans are collected into 6-packs or 12-packs and overwrapped in shrink film. The multi-packs then pass through a shrink tunnel where hot air circulates uniformly around the film, causing it to contract tightly without damaging the product inside. Packaged units are routed to case packing stations. Here, automatic erectors construct corrugated cases from flat blanks using glue or tape. Robotic loaders with vacuum end effectors pick up groups of bottles or cans and place them into the open cases in pre-programmed formations. The filled cases are sealed at the top using either hot melt adhesive applicators or pressure-sensitive tape dispensers. Cases proceed to palletization. Empty pallets are dispensed from a stack onto a conveyor. A layer-forming system organizes cases into a stable pattern using motorized guides and pusher arms. A robotic palletizer or gantry system transfers each layer onto the pallet, adjusting height and position after each pass. Between layers, slip sheets may be inserted to enhance stacking integrity. Once fully stacked, the pallet is moved into a stretch wrapping station. A rotating turntable spins the pallet while a film carriage moves vertically, wrapping the entire stack in tensioned polyethylene film to secure the load. The Canada Dry production process begins with the intake and treatment of raw water. Municipal water is directed into a series of pre-treatment systems through stainless steel pipelines. The first step is mechanical filtration, where water flows through mesh strainers that remove coarse particulates. Following this, it passes through a dual media sand and anthracite filtration system to eliminate finer suspended solids. The next stage is activated carbon filtration. As the water moves slowly through the carbon beds, chlorine, chloramine, and organic contaminants are removed through adsorption. The water is then softened using a sodium-based ion exchange system that exchanges calcium and magnesium ions for sodium ions, reducing scale formation in downstream equipment. After softening, the water is subjected to reverse osmosis using high-pressure pumps to force it through semi-permeable membranes that separate out dissolved solids, bacteria, and unwanted ions. The treated water then undergoes ultraviolet sterilization and sub-micron filtration to achieve microbiological purity before being transferred to agitated, sealed stainless steel storage tanks for use in the product blend. Parallel to this, the syrup production begins in a closed system syrup room. Liquid sweeteners, such as high fructose corn syrup, are delivered in heated tankers and pumped into bulk storage silos lined with food-grade coatings. These silos are equipped with volumetric flow meters and thermal controls. The sweetener is metered into stainless steel mixing vessels using precision dosing pumps. These vessels are jacketed for thermal regulation and include bottom-mounted mixers driven by variable frequency motors to achieve high shear mixing. Ginger extract, lime oil, lemon oil, and proprietary spice emulsions are stored in temperature-controlled dosing cabinets and delivered via sealed piping to the blending tanks. Dosage is governed by recipe management software, with peristaltic pumps calibrated for microdosing accuracy. Citric acid is introduced to provide tartness, followed by potassium sorbate or sodium benzoate as preservatives. Caramel color, if used, is injected through positive displacement pumps, controlled to a fraction of a milliliter per liter. Once all components are in the tank, the syrup undergoes a high shear mixing cycle. After homogenization, it is flash pasteurized by pumping through a plate heat exchanger system, reaching temperatures above 85 Stiktig for a few seconds, and then rapidly cooled using a countercurrent chilling loop. The syrup is passed through sterile filters and transferred into insulated holding tanks with nitrogen blankets to prevent oxidation and maintain flavor integrity. With syrup and water prepared, they are combined using an inline blending system. This unit uses magnetically driven flow meters to monitor real-time volumetric flow of each stream. PID-controlled valves adjust the ratio continuously to maintain the programmed syrup-to-water proportion. The blend passes through a series of mixing chambers where turbulence is created using static mixers to ensure full molecular integration. An inline refractometer measures the resulting Brix level, and adjustments are made automatically to ensure target sweetness is met within plus 0.1 Brix. After blending, the mixture is deaerated in a vacuum vessel. Liquid enters a chamber under reduced pressure, causing entrained oxygen and other gases to escape. The deaerated product is immediately cooled through a glycol-based plate chiller to a temperature just above 0 degrees Celsius, maximizing carbon dioxide solubility in the next step. The cold, deaerated blend is sent to the carbonation module. Here, liquid CO2 is introduced into the beverage via high-precision sparging rings located at the base of the carbonation tank. The tank operates under constant high pressure and uses recirculation pumps to keep the liquid moving over the gas interface, improving dissolution rates. Carbonation levels are controlled through feedback loops tied to gas volume analyzers that measure dissolved CO2 in real time. Once carbonated, the product is routed through pressurized transfer lines to filling buffer tanks. These tanks maintain positive pressure to prevent gas loss and are fitted with level sensors and pressure regulators. container preparation runs in parallel. Empty aluminum cans or PET bottles are delivered via automated depalletizers that use vacuum pads or mechanical sweep arms to remove layers of containers and place them on conveyor systems. The containers pass through a cleaning unit where they are inverted and rinsed internally with filtered, ionized air or sterile water. Any residual moisture is blown off using high-velocity air knives. Clean containers proceed to the filling carousel. The filling system consists of a rotary filling machine with 60 to 120 heads, depending on capacity. Each container is raised into position against a filling valve. The system first applies counter pressure to match internal carbonation levels and prevent foaming. Filling valves open when pressure equalization is achieved. Product flows into the container through gravity or gentle pressurization. During fill, displaced gas vents through a return tube to maintain equilibrium. Fill volume is controlled by valve timing or volumetric flow measurement. Once filled, the valve closes and the container is lowered back to the conveyor. Capping occurs immediately after filling. For bottles, closures are delivered by an oriented cap feeder using centrifugal force. Caps are guided into a chute and pressed onto bottles by servo-controlled capping heads with adjustable torque settings. For cans, aluminum ends are fed into place from a lid magazine. A seamer head performs a double-fold operation, curling the lid's flange over the rim of the can and compressing the metal layers together to form an airtight seal. Sensors verify each seal, and containers with improper application are ejected from the line. Filled and sealed containers are conveyed through a vision inspection system equipped with high-speed cameras and LED backlighting. Algorithms analyze fill height, cap placement, and label orientation. Infrared sensors check for proper internal pressure via deformation profiles. Containers that do not meet specification are removed from the line using pneumatic pushers. Labeling systems vary by format. PET bottles pass through wraparound labelers that apply pressure-sensitive or roll-fed film labels. Servo motors control label placement, while rubber rollers press labels onto the surface. Cans use shrink sleeve applicators, where sleeves are dropped over the container body and pass through a heat tunnel. The tunnel uses either infrared or steam heat to contract the film evenly around the can. Label inspection units verify barcode readability, positioning, and design accuracy. The finished containers are then grouped into multi-packs. Bottles are sorted and arranged into clusters using pneumatic sweep arms and placed into molded plastic carriers or corrugated trays. Cans are conveyed into shrink wrapping units, where sets of 6, 12, or 24 are collated onto a moving belt. Polyethylene shrink film is dispensed over the groups and sealed at the edges. The packages move through a heated tunnel with recirculated hot air that shrinks the film tightly around the cans, securing them in a stable bundle. Multi-packs advance to the case packing area. Automatic case erectors unfold corrugated blanks into boxes and place them on a conveyor. Robotic gantries fitted with suction grippers pick up multiple multi-packs at once and lower them into open cases. Depending on format, cases may be closed using tape applicators or hot melt glue systems. Completed cases are scanned for contents, weight, and closure integrity using inline check weighers and vision systems. Palletizing begins with pallet dispensing. Wooden or plastic pallets are fed from a vertical stack onto a chain conveyor. Robotic palletizers equipped with multi-axis arms arrange cases on the pallet in interlocking patterns to maximize stability. Slip sheets may be inserted between layers using vacuum pick-and-place units. Once stacking is complete, the pallet moves into an automatic stretch wrapper. Here, the pallet is spun on a turntable while a film carriage applies tensioned polyethylene film around the load. The film is heat sealed at the end of the cycle, and the wrapped pallet is discharged to a staging conveyor. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then, the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems. allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. Most people have no idea how these sodas are actually made in factories. Behind Dr. Pepper, Sprite and Canada Dry are hidden factories and secret formulas transforming raw ingredients into billions of bottles every year. In this documentary, we take you inside the production lines to uncover each step from flavor creation to high-speed sealing, revealing the surprising science behind every sip. Dr. Pepper production begins with water purification. Incoming municipal water is first passed through a series of coarse filters to remove sediment and particulates. It then flows into a multi-stage filtration system, including activated carbon beds that strip away chlorine, organic compounds, and any residual taste or odor. The water is then softened through ion exchange columns that extract calcium and magnesium. Finally, the water passes through reverse osmosis membranes operating at high pressure, forcing the liquid through semi-permeable membranes that eliminate dissolved solids, heavy metals, and microorganisms. The purified water is collected in stainless steel holding tanks, agitated continuously to maintain consistency and prevent stagnation. Concurrently, concentrated syrup production begins. This involves a precise blend of liquid sweeteners, flavor concentrates, acidulants, and coloring agents. High fructose corn syrup or liquid sugar arrives in tanker trucks and is pumped directly into insulated storage silos. From there, metering pumps draw exact amounts of sweetener into stainless steel mixing vessels. Each vessel is jacketed for temperature control and fitted with high-speed impellers. Flavor compounds are stored in temperature-regulated vats and dispensed in minute quantities using servo-controlled dosing systems. Each component is added in a fixed sequence to ensure homogenization and prevent chemical interaction before full dilution. Citric and phosphoric acid are added next via automated dosing units, lowering the pH and adjusting taste profile. Caramel color is injected through pressurized nozzles in measured bursts, darkening the mixture. After all ingredients are blended, the syrup passes through a plate heat exchanger for flash pasteurization. Heated to above 85 degrees Celsius for under 30 seconds, the syrup is then rapidly cooled to preserve flavor integrity. The syrup is piped into chilled storage tanks, each lined with food-grade epoxy to prevent contamination. These tanks are agitated at controlled RPMs to keep the syrup uniform. From this point, the syrup is mixed with the purified water. This occurs inside a continuous blending unit known as a proportioner. The unit draws both syrup and water in a 1:5 ratio using synchronized flow meters and magnetically actuated valves. Flow rates are adjusted dynamically based on inline refractometers that monitor sugar concentration in real time. Any deviation from target Brix level results in automatic recalibration of fluid inputs. The mixture then enters a deaeration chamber where it is subjected to vacuum pressure to remove entrained oxygen and carbon dioxide, which can affect taste and carbonation efficiency. Following deaeration, the liquid enters a carbonator. Inside a sealed stainless steel vessel, the beverage is chilled to near freezing temperatures to increase gas solubility. Liquid carbon dioxide is injected into the drink through a diffuser plate with thousands of microperforations. The gas dissolves rapidly under high pressure, saturating the beverage with carbonation. Rotary carbon pumps recirculate the liquid within the chamber to ensure uniform CO2 distribution. Carbonation levels are continuously monitored by inline gas volume analyzers. The carbonated beverage is held in pressurized buffer tanks awaiting transfer to the filling line. The filling process begins with bottle or can preparation. Empty containers arrive via conveyor belts in nested stacks or crates. A depalletizer equipped with vacuum grippers lifts layers of containers and places them onto the in-feed conveyor. Containers proceed through a rinser unit that inverts each one and blasts filtered air or sterile water inside to dislodge debris. The containers are then uprighted and transferred to the filler carousel. The filling machine features multiple heads, typically between 40 to 120, arranged in a rotary configuration. Each head is fed from the pressurized carbonated beverage tank. As a container aligns with a filling head, it is clamped and sealed. Counterpressure is applied to prevent foaming. A filling valve opens and the product is gravity-fed or gently pumped in. As the container fills, vent tubes displace internal gas to maintain pressure equilibrium. Once full, the valve closes and the container is released. Immediately after filling, containers proceed to the capping station. In bottle lines, caps are sorted and oriented using centrifugal feeders. Each cap is dropped into position and pressed onto the bottle using pneumatic or servo-controlled spindles. Torque sensors ensure proper seal strength. For cans, lids are fed through chutes and placed atop the can mouth. A seaming head engages, folding and curling the lid's edge around the can's rim to create a hermetic seal. The container is then released to a discharge conveyor. Sealed containers pass through an inline quality control system. High-speed vision sensors inspect each container for correct fill height, cap application, label alignment, and structural integrity. Any defective item is ejected via air-jet nozzles. Simultaneously, select containers are diverted for destructive testing. These include pressure retention tests, carbonation level checks using digital pierce testers, and torque measurements for closure tightness. Approved containers proceed to labeling. Bottles pass through a label applicator fitted with servo-driven rollers. Pre-printed labels on adhesive rolls are cut and transferred using vacuum drums. Each label is wrapped and smoothed onto the bottle's surface using motorized brushes. Can lines use shrink sleeve applicators? Sleeves are dropped over the cans and pass through a heat tunnel where forced air heaters contract the film around the container body with uniform tension. Each labeled item is scanned by barcode readers to verify correct SKU association. Labeled products travel to the packaging area. Containers are grouped into multi-packs using high-speed collators. For bottles, robotic arms or pneumatic sweepers push groups of 6, 12, or 24 into cardboard carriers or plastic overwrap. For cans, shrink film machines envelop the groupings with polyethylene film. The packs pass through shrink tunnels where the film tightens around the cans. Heat is applied via convection blowers at calibrated temperatures to avoid deformation. Finished multi-packs are conveyed toward case packing stations. Corrugated cartons are erected from flat blanks by automated formers and transported via belt to loading stations. Pneumatic. Pushers slide each multi-pack into its case. In robotic systems, Delta robots or articulated arms equipped with suction grippers lift and place products with extreme precision, adjusting in real time for orientation variances detected by machine vision. Loaded cartons proceed to automatic tapers that seal the top flaps with pressure-sensitive adhesive tape or hot melt glue. Sealed cases continue to the palletizing area. Pallet dispensers drop wooden or plastic pallets onto powered rollers. A layer building system positions cases in pre-programmed patterns for structural stability. Robotic arms or gantry-style palletizers pick cases and place them in rows, adjusting height via vertical actuators. Each layer may be interleaved with a slip sheet for added stability. Once a pallet is complete, a wrapping station envelops it in stretch film. The turntable spins while a vertical arm applies film under tension, binding the load tightly. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes, charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe to supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck, and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats, open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100 degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 5% of its volume to evaporation. Maturation time varies by product. Old Number 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniels because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old Number 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniels is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labeling runs to comply with EU, UK, or Asian labeling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniels uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature Fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. Nescafe instant coffee is produced by extracting soluble coffee solids from roasted beans and then drying that extract into stable granules that dissolve fast in water. The process begins with green coffee beans that are cleaned to protect the downstream grinders and roasters. The beans pass over screens that remove stones and oversized debris. Air classifiers lift away light husk fragments and dust. Magnets capture metallic fragments before the beans enter storage bins. Roasting converts the raw beans into a brittle aromatic material that can be milled and extracted. Bins into a roaster at a controlled mass flow. Heat is applied in a programmed curve that drives moisture out first. As temperature rises, the beans expand and internal pressure opens micropores. Sugars and amino acids react and form brown polymers that deepen color. Volatile aroma, compounds form and migrate toward the surface as the bean structure becomes porous. Roast control is managed by time and temperature and airflow. Airflow carries away smoke like volatiles and maintains uniform heat transfer. Roast endpoint is set to balance extraction yield and flavor profile. A lighter roast preserves brighter notes but can reduce solubility. A darker roast increases solubility but can add bitter roast solids. When roasting ends, the beans are cooled quickly to stop further reactions. Cooling air flows through a moving bed, so the beans drop below reaction temperature. Rapid cooling limits over roast drift and protects aroma. The cooled beans move into a degassing period where trapped gases begin to leave. Degassing reduces foaming and pressure issues in extraction. Grinding sets the surface area that controls extraction speed and selectivity. Beans are conveyed to roller mills or hammer mills depending on target particle shape. Roller mills crack and shear the beans into a controlled distribution. Hammer mills impact the beans and can create more fines. The grinder is tuned to create particles that allow fast water penetration, yet avoid excessive fines that clog filters. Particle size is classified after grinding. Screens and air classifiers separate fines from the main fraction. Oversized particles are returned to the grinder. The goal is a narrow band that supports stable extraction bed permeability. A stable bed keeps water flow even and prevents channeling. Extraction is the heart of instant coffee production. Ground coffee is loaded into extraction columns that operate as a countercurrent system. Hot water enters one end of the column train and spent grounds exit the other end. Fresh water meets the most exhausted grounds first. Water becomes progressively richer as it moves toward fresher grounds. Extraction temperature is set to dissolve desired solids while limiting harsh compounds. Higher temperature increases yield and dissolves more bitter fractions. Lower temperature preserves aroma but reduces yield. The system often uses stage temperatures across the column train. Early stages may run hotter for bulk solids. Later stages may run cooler to protect delicate notes. Pressure is used to keep water in liquid form at elevated temperatures. Pressurized extraction improves heat transfer and solubility control. Flow rate is regulated to maintain a target contact time. Contact time controls how far extraction proceeds before the liquid leaves the bed. Too short a contact time wastes soluble solids. Too long a contact time pulls more bitter fractions. The extract leaving the columns contains dissolved coffee solids and suspended, fine particles. Clarification removes those particles to improve final appearance and stability. The extract passes through screens that catch coarse fines. It then enters a centrifuge that separates suspended solids by density. Clarified extract flows forward, while sludge is removed for separate handling. Fine filtration can follow centrifugation. Depth filters capture remaining microfines that would create haze. Filter choice balances clarity and flavor. Too aggressive filtration can strip flavorful colloids. Too little filtration can leave sediment in the final granules. At this point, aroma management becomes important because extraction and clarification drive off volatile compounds. Many lines capture aromatics from roasting and grinding and early extraction vents. These aromatics are condensed into an aroma concentrate. The concentrate is stored cold to slow loss. It is added back later after drying or near the end of concentration. The clarified extract is still mostly water, so it must be concentrated. Evaporation removes water and raises solids content. Concentration is usually done under vacuum, so boiling occurs at lower temperatures. Lower boiling temperatures reduce thermal damage and preserve flavor. Falling film evaporators are common because they expose liquid as a thin film. Thin films evaporate fast and limit residence time. Solids concentration is controlled to a target viscosity suitable for drying. Too low a solids level wastes energy in drying. Too high a solids level becomes too viscous to atomize in a spray dryer. Sensors track density and refractive index as proxies for solids. Flow control keeps the evaporator steady so the concentrate remains consistent. Some product streams include a mild heat treatment during concentration. This can stabilize the concentrate by inactivating enzymes and reducing microbial load. The heating profile is kept brief to avoid cooked notes. Vacuum evaporation already reduces thermal stress, so the heat treatment can be minimal. After evaporation, the concentrate is cooled to a controlled temperature. Cooling protects aroma and sets viscosity for the selected drying method. The process then splits depending on whether the line makes spray-dried coffee or freeze-dried coffee. Spray drying converts concentrate into powder by atomizing it into hot air. The concentrate is pumped to an atomizer that forms fine droplets. A rotary wheel atomizer can create a narrow droplet size band. A pressure nozzle atomizer can create different droplet distributions. Droplet size controls final particle size and bulk density. Droplets enter a drying chamber with heated air. Water evaporates from the droplet surface first. A skin forms, and then moisture diffuses outward through the skin. The droplet shrinks and solidifies into a particle. Air temperature is controlled, so drying is rapid but not scorching. Outlet air temperature is a key indicator because it reflects remaining moisture. Powder leaving. The drying chamber is separated from air in cyclones. Cyclones spin the airstream and throw particles outward. Fine particles are captured efficiently and then discharged. Additional bag filters capture the finest dust. The recovered powder is cooled to prevent caking. Final moisture is set low enough for stability, but not so low that particles become overly fragile. Spray-dried powder can be too dusty and too fast dissolving. Many lines agglomerate it to create larger porous granules. Agglomeration starts by re-wetting powder lightly with steam or water mist. Particles become tacky on the surface. They collide and stick into clusters. Warm air then dries the clusters and locks in the structure. The resulting granules have larger size and better sink behavior in water. Freeze drying follows a different path that preserves aroma and creates crisp granules. Concentrate is first chilled and then frozen into a solid slab or into pellets. Freezing speed controls ice crystal size. Larger ice crystals create larger pores after sublimation. Smaller ice crystals create finer pores and can slow dissolution. Frozen coffee enters a vacuum freeze dryer. Under vacuum, the ice sublimates, which means it goes from solid to vapor without melting. Heat is added gently through shelves or radiant plates. Sublimation leaves behind a porous matrix of coffee solids. The structure is brittle and breaks into irregular granules. After freeze drying, the dried slab is milled or fractured into target granule size. Screening separates fines and oversize. Oversize is reduced further. Fines can be recycled into agglomeration or blended depending on product targets. The granules are then conditioned to equalize moisture and temperature. Aroma restoration is typically applied after drying because high heat and vacuum remove volatiles. Aroma concentrate is dosed onto the dry granules in a closed blender. The granules tumble while a fine spray coats their surfaces. The coating is absorbed into pores and binds by capillary action. The system controls spray rate to avoid wet spots that cause clumping. Some lines also perform a light surface polishing. This step reduces dust and improves flow in packaging. Polishing can be done by gentle tumbling that knocks off loose fines. It can also include a tiny amount of food-grade anti-caking agent. The application is kept minimal, so it does not change flavor release. Quality control at this stage focuses on moisture and bulk density and dissolution time. Moisture affects shelf stability and clumping. Bulk density affects dosing in jars and sticks. Dissolution time affects consumer experience in hot and cold water. Particle size distribution is measured because it controls flow and dust. Blending is used to keep flavor consistent across production lots. Granules from different runs can be blended to average variations. Blending equipment uses gentle paddles to avoid crushing. The blender also equalizes aroma addition across the batch. Sampling confirms uniformity by checking aroma intensity and color and soluble solids. Nesquik chocolate drink mix is manufactured by turning cocoa and sweetener into a free-flowing instant powder that wets fast and disperses without floating clumps. Production starts with bulk ingredient receiving and conditioning. Sugar arrives as granulated crystals and moves into silos with controlled humidity. Cocoa powder arrives in lined totes and is kept in a dry room to prevent caking. Milk-derived powders can be included for creaminess, and they are stored cold enough to stay free-flowing. Minor ingredients like salt and flavors arrive in sealed drums to protect aroma strength. Vitamin and mineral premixes arrive as low-dose powders that require tight segregation for accurate dosing. The line begins with particle preparation because every downstream step depends on predictable flow. Sugar is screened to remove oversized crystals that can separate during blending. Sugar fines are managed because excessive fines increase dust and can make the mix pack too tightly. Cocoa is sifted through vibratory screens to break soft agglomerates. Any fibrous lumps are removed to prevent specks in the final product. Milk powders are sieved with larger mesh to protect fragile particles from unnecessary grinding. Cocoa powder requires special handling because it is hydrophobic and tends to float. The powder surface contains natural fats that repel water. This property is the main reason Nesquik needs instantizing steps. The process, therefore, focuses on building granules that pull water in quickly. It also focuses on adding emulsifiers that lower surface tension and improve wetting. Weighing and batching starts once each ingredient is within specification. Large-scale ingredients are metered by loss in weight feeders. The feeders deliver sugar and cocoa at controlled rates into a pre-blend hopper. Medium-scale ingredients like milk powder and maltodextrin are metered through secondary feeders. Very low-dose ingredients like vitamins are added through micro feeders with screw dosing. Each feeder is calibrated so the recipe ratio stays stable across long runs. Pre-blending is used to prevent micro-ingredient streaks. Sugar becomes the carrier phase because it has high mass and flows well. Micro-ingredients are first blended with a small portion of sugar in a ribbon blender. This creates a dilute premix with uniform distribution. The premix then rejoins the main sugar stream and reduces the chance of hot spots. The main blending step combines sugar and cocoa into a uniform base. A high-capacity ribbon blender or plowshare mixer is common here. The mixer creates strong folding action that lifts powder and then lets it fall through a shear zone. Cocoa is dispersed into sugar so the color becomes even. Mixing time is controlled because overmixing can create electrostatic charging and dust. Undermixing leaves cocoa streaks that show up as dark clusters in scoops. Flavor addition happens during the main blend or just after it. Vanilla flavor is often added as a liquid or as a dry encapsulated powder. Liquid flavor is sprayed through a fine nozzle into the moving powder bed. The spray rate is low to avoid creating wet clumps. The mixer speed is increased briefly to distribute the liquid film. Dry flavor powders are easier to distribute, but they still need good agitation to avoid pockets. Salt is added in small quantity, and it must be dispersed evenly. Salt crystals can segregate if their size differs from sugar. Many lines use fine salt or salt dissolved into a small liquid addition. When salt is added as a dry powder, it is often included in the premix step. This reduces segregation later in transport. If the formula includes vitamins, the process emphasizes gentle but thorough distribution. Vitamin premixes can be sensitive to heat and moisture. They are added after any warm steps to reduce loss. They are also protected from intense shear that could break protective coatings. The blender uses a defined sequence so the vitamins are introduced after the bulk powders have already become uniform. At this stage, the powder is blended, but it still has poor instant properties. Cocoa will still float and form islands on water. The next stage is instantizing, which converts fine powders into porous granules that sink and disperse. There are several ways to instantize. A common route is agglomeration with a wetting step followed by drying and cooling. Agglomeration starts by feeding the blended powder into a controlled chamber. The powder forms a moving curtain or a fluidized bed. A binder is then applied as a fine mist. The binder can be water or sugar syrup depending on the target density. The binder lightly wets particle surfaces and makes them tacky. Tacky particles collide and stick into clusters. These clusters grow into granules as more powder adheres. Granule growth must be controlled tightly. If binder is too high, the granules become large and hard. If binder is too low, the granules remain dusty and fragile. Airflow and chamber turbulence control collision rate. Residence time controls final size. The process aims for granules that feel light and porous. Porosity is important because it creates capillary channels that pull in liquid. A key improvement step is lecithination. Lecithin is an emulsifier that improves wetting and reduces surface tension. Lecithin can be applied as a liquid spray onto moving powder. It can also be applied as a solution in a volatile carrier. The spray coats granule surfaces and migrates into pores. This makes cocoa less hydrophobic in the cup. The dosage is low, but the impact on dispersibility is large. When lecithin is applied, the process must avoid creating shiny wet spots. Spray droplets must be small and evenly distributed. The bed must be moving vigorously so the film spreads. Temperature is controlled, so lecithin stays fluid during application. After application, the granules are dried slightly to lock the surface condition. Drying follows agglomeration because binder adds moisture. Drying is done with warm air moving through the granule bed. Air temperature is chosen to remove water without changing flavor. Too much heat can drive cocoa volatiles off and dull aroma. Too little heat leaves moisture that causes caking in the jar. The dryer controls inlet temperature and outlet humidity to reach a target moisture. Drying also stabilizes structure. As moisture leaves, the binder creates bridges between particles. These bridges set granule strength. Strong enough bridges prevent breakdown into dust. Weak bridges create fines during conveying and filling. The process tunes drying time to meet a target crush strength. That crush strength must still allow fast dissolution in the cup. After drying, the product is cooled. Cooling prevents condensation in packaging and reduces clumping risk. Cooling air is dehumidified, so it does not add moisture. The granules exit at a temperature close to the packaging room temperature. This prevents moisture migration when the product enters sealed packs. Screening and sizing occur after cooling. Vibratory screens remove oversized agglomerates that would dissolve slowly. Screens also remove fines that create dust and poor wetting. Oversize can be milled lightly and returned to agglomeration feed. Fines can be recycled as seed material for new agglomeration. Recycling is controlled, so the powder does not build up too much fine content. Some lines add a final dry blend step after agglomeration. This can be used to add heat-sensitive vitamins. It can also be used to add a small amount of anti-caking agent. Anti-caking agents are used at very low levels to keep flow stable. They are distributed with gentle mixing to avoid breaking granules. The blend time is short to protect structure. Density control is a major target for drink mixes. Bulk density affects spooning and packaging, volume and consumer dosing. Agglomeration tends to lower density because it creates porous granules. The process tunes binder and airflow to hit a defined density band. Too low, a density makes scoops inconsistent. Too high a density can reduce instant performance. Flowability control is equally important. Granules must flow through hoppers without bridging. They must also settle consistently in jars. Flow is improved by uniform granule size and low moisture and smooth surfaces. Excess fines degrade flow because they increase cohesion. The screening stage, therefore, has a strong influence on packaging efficiency. Color uniformity is checked because cocoa distribution must remain stable. Color drift can indicate segregation or inadequate mixing. If the product includes added micronutrients, the line checks distribution by sampling and chemical analysis. Uniform distribution is achieved mainly by the premix approach and by stable blender loading. The product then moves to packaging feed systems. Gentle conveyors are used to protect granules from breakage. Bucket elevators can be used with low drop heights. Pneumatic conveying is possible, but it can create fines if velocities are high. When pneumatic systems are used, the line uses low velocity dense phase conveying. Bends are designed with large radii to reduce impact. Packaging for Nesquik can be in jars or canisters or sachets. For canisters, the product is filled by volumetric auger fillers. The auger rotates and dispenses a controlled volume of granules. The fill weight depends on bulk density, so density must remain stable. Check weighers confirm the filled mass and reject outliers. The canister is then capped with controlled torque to maintain a moisture barrier. Starbucks coffee starts as green beans that are transformed by controlled roasting, rapid cooling, precision grinding, and oxygen-managed packaging so flavor remains stable until brewing. Green beans arrive as a hard, dense seed with moisture-locked, inside cell structure. The first job is cleaning because even small hard contaminants can damage rollers and grinders. The beans pass through screens that remove stones and broken fragments. Air separation lifts away chaff and dust. Magnets capture metallic particles before the beans enter storage bins. Storage is designed to keep bean moisture and temperature steady. Beans are blended from different lots to hit a target profile before roasting begins. This blending step is a physical averaging process. It reduces variability in density and moisture that would otherwise shift roast development. Roasting begins with accurate feed control. Beans enter a roaster at a fixed mass rate, so heat transfer remains consistent. Hot air and heated metal surfaces raise bean temperature in a staged curve. Early roasting drives off free moisture. Steam leaves the bean and pressure builds inside pores. The bean structure expands and becomes more porous as internal water turns to vapor. As temperature rises further, chemical reactions generate color and aroma precursors. Sugars and amino acids react and produce brown polymers that deepen color. Oils migrate toward the surface as the bean matrix opens. Gases form inside the bean and create internal pressure that changes cracking behavior. The roast curve is adjusted so reactions progress without scorching the exterior. Airflow is a main control lever during roasting. Higher airflow increases convective heat transfer and carries away smoke like volatiles. Lower airflow increases contact time of vapors and can intensify roast notes. Exhaust control keeps the roast environment stable, so each batch follows the same thermal history. The roast endpoint is defined by bean temperature and time at development conditions. A shorter development phase preserves brighter notes but can reduce solubility. A longer development phase increases solubility and roast character. The endpoint also influences how easily the bean grinds. A darker roast fractures more easily and produces more fines at the same grinder setting. When the endpoint is reached, the beans must be cooled fast. Cooling stops reactions that would continue from residual heat. Beans drop into a cooling tray or a cooling conveyor. High airflow pulls heat out rapidly and reduces carryover roasting. The target is a uniform final bean temperature, so later packaging does not trap heat and create condensation. After cooling the beans, enter a degassing phase. Roasted beans contain carbon dioxide trapped in pores. Degassing releases gas gradually and changes how the coffee behaves in packaging. If beans are packed too soon, pressure can build inside bags. If beans degar too long, the most volatile aromas can decline. The process chooses a defined rest window that balances gas release and aroma retention. Quality sorting can occur after cooling. Optical sorting can remove scorched beans and pale beans. Density sorting can remove light defects that roast differently. This step tightens consistency in the final bag because even a small number of off beans can alter brewed cup perception. From this point, production splits into whole bean and ground coffee paths. Whole bean coffee moves toward packaging with minimal mechanical stress. Ground coffee requires additional size control because particle distribution defines extraction speed in the brew. Grinding begins with grinder selection based on product format. Roller mills produce a more uniform distribution with fewer extreme fines. Burr-style industrial grinders create a controlled cut with predictable heat generation. Grinder settings define the median particle size and the tail of fines. The fines fraction matters because it drives bitterness and slows flow in filter brewing. Temperature control during grinding protects aroma and reduces clumping. Grinding generates heat from friction and impact. If coffee warms, too much volatile compounds flash off. Warm grounds also pack and bridge more easily in hoppers. The line manages temperature by controlling throughput and by using cooled air or staged grinding. After grinding, the coffee is classified. Vibratory screens or air classifiers remove oversized fragments and reduce the fraction of dust. Oversized fragments can be returned to the grinder. Excess dust can be blended into other streams in controlled amounts or removed depending on target. Classification improves brew repeatability and improves fill accuracy in packaging. Aroma management becomes more critical once coffee is ground. Grinding exposes fresh surface area and accelerates oxidation. The process, therefore, reduces oxygen exposure time between grinding and sealing. Conveying is often enclosed and may use inert gas in certain steps to reduce oxygen pickup. The goal is to keep oxygen away from oils on particle surfaces. Packaging is built around barrier films and controlled headspace. Bags or canisters are formed and then filled by weight. Auger, fillers, and vibratory feeders deliver grounds in measured pulses. Fill chutes are designed to reduce dust and keep seal areas clean. Weight checks confirm each unit meets target. For whole bean bags, the filler drops beans gently to avoid fracturing. Fractured beans create fines at the bottom of the bag. They also create more surface area for oxidation. Drop heights are minimized and chutes use smooth curves rather than sharp bends. Many coffee bags use a one-way degassing valve. The valve allows carbon dioxide to escape without letting oxygen in. This supports earlier packaging because gas can leave after sealing. It also reduces bag swelling during distribution. Valve application is done as part of bag manufacturing or as an inline step before filling. Sealing closes the package and locks in the controlled atmosphere. Heat seals must be strong and continuous. Seal jaws apply temperature and pressure for a defined dwell time. If dust sits in the seal zone, the seal can leak. The line, therefore, controls dust by extraction and by nozzle cutoff design. Once sealed, the packages move through coding and inspection. Vision systems can confirm seals and valve presence. Check weighers confirm net weight. Metal detection can be used as a final protection step. Units are then packed into cases with orientation that protects valves and reduces crushing. Dairy Queen ice cream begins with the formulation of a liquid ice cream mix that contains a specific balance of milk solids, butterfat, sweeteners, stabilizers, and emulsifiers, all designed to create a product with a soft serve texture, rich flavor, and the structural integrity to hold shape when dispensed at below freezing temperatures. The process starts with the metering of liquid ingredients into a high-capacity stainless steel mixing tank. Milk, cream, and liquid sweeteners, such as corn syrup, are pumped from refrigerated storage tanks using automated pumps that are controlled through a programmable logic controller system. The precise volumes are determined by batch recipes that are stored digitally and loaded into the mixing unit via operator interface panels. Dry ingredients like skim milk powder, dextrose, and stabilizer emulsifier blends are added through a dry powder feeder positioned over the mixing tank. As the powders are introduced, high-speed impellers and rotor-stator mixers circulate the mixture, dispersing solids uniformly and ensuring the base is homogeneous. This initial mix is agitated continuously for a set period until the solution reaches a uniform temperature and particle distribution. Once mixed, the liquid ice cream base is pumped through a series of inline filters to remove any clumps, undissolved particles, or foreign matter before proceeding to the pasteurization stage. Pasteurization is a critical thermal process that ensures microbiological safety and improves the mixer's ability to support uniform freezing and aeration. The base mix is pumped through a plate heat exchanger system, which uses hot water or steam on one side of the stainless steel plates and the ice cream mix on the other. The two fluids never touch, but heat is transferred efficiently across the metal surfaces. The mix is quickly heated to a target temperature, typically around 80 to 85 degrees Celsius, and held at that temperature for a predetermined number of seconds, usually no more than 25, before being rapidly cooled to below 4 degrees Celsius using chilled water or glycol solution in the next section of the exchanger. The rapid heating and cooling prevent unwanted protein denaturation while killing potential pathogens. The chilled, pasteurized mix is then transferred to an aging tank. These tanks are large, insulated stainless steel vessels equipped with slow-speed agitators that maintain gentle circulation without incorporating air. The mix is aged for a minimum of 4 hours, often overnight, to allow the fat crystals to partially solidify and the stabilizers and emulsifiers to fully hydrate. This aging process improves body, creaminess, and melt resistance of the final product and ensures a consistent structure when the mix is frozen later. After aging, the liquid mix is pumped into a continuous freezer. This is where the transformation from liquid to frozen soft serve occurs. The continuous freezer is a high-efficiency, jacketed stainless steel cylinder containing a rotating scraper blade assembly and a direct expansion refrigeration jacket filled with ammonia or another refrigerant. As the mix enters the chamber, it is chilled to approximately 6 to 8 degrees Celsius while being whipped rapidly by the rotating blades. This mechanical action accomplishes two things at once. It freezes the water content of the mix into fine ice crystals and incorporates air into the structure to create overrun. Overrun is the term used to describe the volume of air introduced into ice cream, expressed as a percentage of the original mix volume. Dairy Queen soft serve typically has a controlled overrun around 45%, meaning 100 liters of base mix will become 145 liters of finished product. This air is crucial for texture, mouthfeel, and lightness. It is injected through filtered nozzles as the blades churn the mixture. The balance of air and ice must be tightly regulated. Too much air leads to foaminess, while too little creates a heavy, dense product that doesn't dispense smoothly. The frozen, aerated soft serve exits the continuous freezer at a semi-solid state and is transferred immediately into sterile holding tanks or directly into distribution containers, depending on the factory design. In larger operations, the soft serve may be pumped into pre-chilled, bag-in-box containers made of multi-layered, food-safe plastic film that protects the product from light and moisture. Each bag is filled by volume through a no-drip valve, sealed mechanically, labeled with a production code and expiration date, and moved to refrigerated storage. In other systems, the soft serve may be routed into pressurized stainless steel kegs or bulk plastic drums equipped with quick connect couplings for easy installation at the retail dispenser level. These containers are filled in clean rooms under positive pressure airflow to eliminate airborne contamination. The filled containers are immediately stored at sub-zero temperatures in blast freezers or walk-in cold rooms set to maintain the product just below the freezing point without hardening the mix entirely. From here, the frozen product is shipped in refrigerated trucks to the point of sale, typically a retail location equipped with a dedicated soft-serve dispensing machine. These machines are miniaturized versions of the industrial continuous freezer used in the factory. Each machine contains a hopper that holds the soft-serve mix, an auger or scraper blade assembly, and a narrow freezing cylinder cooled by either air or water-based refrigeration systems. When the machine is activated, the product is pulled from the hopper into the freezing cylinder where it undergoes a final freezing and aeration stage. The mix is chilled further to about 9 degrees Celsius while the blades whip it to preserve consistency. When the lever on the dispenser is pulled, the pressurized frozen product is extruded through a specially designed nozzle that imparts the signature spiral swirl to the ice cream as it is dispensed into a cone or cup. Each part of this process, from raw milk to cone, relies on tightly controlled mechanical parameters, time-sensitive transitions, and a closed system design that ensures the finished Dairy Queen soft serve has a consistent texture, smooth pour, and creamy mouthfeel. The cooling cycles, flow rates, agitation speeds, syrup-to-air ratios, and thermal profiles are all digitally monitored at every stage using PLCs, sensors, thermocouples, and SCADA systems. Adjustments are automated to keep the output within strict tolerances. To ensure quality, samples are pulled at multiple points in the process for physical, chemical, and microbiological testing. These include fat content analysis using infrared spectroscopy, overrun verification using displacement methods, viscosity measurement through flow cups or rotational viscometers, and sensory testing by trained tasters who evaluate mouthfeel, melt profile, sweetness, and aftertaste. Sanitation procedures are carried out daily or between batches. All pipes, valves, hoses, and tanks in the mix production system are cleaned in place using automated CIP systems that cycle through pre-rinse, caustic wash, acid rinse, and final sanitizing steps. Soft serve dispensers at the retail level are cleaned manually with specialized brushes and food-safe detergents, followed by complete reassembly and sanitization with hot water flushes to ensure hygiene is maintained without altering the flavor of future batches. Every production batch is traceable by date, time, machine, operator, and ingredient lot, logged in a database that allows for immediate traceback in case of any quality issues. Digital records are kept for regulatory compliance and internal process optimization, helping to refine recipes, extend shelf life, and reduce variability between runs. Bluebell ice cream production begins with the assembly of the ice cream base, which is the liquid foundation used to create every flavor. This base must be smooth, homogeneous, microbially safe, and physically stable throughout the freezing, hardening, and distribution stages. To prepare it, the process starts in a mixing room where stainless steel blending tanks are used to combine raw ingredients such as whole milk, cream, skim milk powder, sugar, corn syrup solids, and stabilizers like guar gum or carrageenan. These ingredients are stored in separate bulk storage silos or tanks at controlled temperatures and are pumped into the mix tank using automated volumetric dosing systems. The control panel interfaces allow operators to select a formula code that precisely dictates the ratios required for each batch. As the ingredients are added to the tank, high shear impellers begin to mix the contents, breaking down solid particles and dispersing fats evenly into the water phase. The temperature is kept in the range of 40 to 50 degrees Celsius to aid solubility and prevent premature thickening. Once mixed into a smooth liquid, the batch is sent through a plate heat exchanger where it is heated rapidly to pasteurization temperatures, usually around 82 to 85 degrees Celsius, and held for 25 to 30 seconds to eliminate any harmful bacteria and extend shelf life. This pasteurization step is monitored using digital sensors that track the flow rate, inlet and outlet temperatures, and holding times. Immediately after pasteurization, the base is cooled just as rapidly by the second half of the heat exchanger using chilled glycol solution or water, dropping the temperature of the mix to around 4 degrees Celsius. This chilled mix is directed into insulated aging tanks where it is gently agitated and held for a minimum of 4 hours. The aging process allows the milk fat to partially crystallize, which improves body and mouthfeel, while stabilizers fully hydrate and develop viscosity. The aging tanks are jacketed and equipped with temperature controllers to ensure the mix stays cold and consistent across the entire volume. From the aging tanks, the base mix is pumped through a filtration unit and into continuous freezers. These freezers are the heart of the transformation process, where liquid mix becomes soft, semi-solid ice cream through a combination of rapid cooling and mechanical aeration. Each freezer consists of a horizontal freezing barrel that's jacketed for refrigeration and fitted with a rotating dasher blade assembly that scrapes the frozen mix from the inside wall while simultaneously blending in air. This air is filtered and injected under pressure to create overrun, the volume of air in the ice cream, which typically ranges from 60 to 90% depending on the product line. The dasher speed and airflow rate are tightly controlled to produce a uniform texture with consistent aeration. As the mix freezes, small ice crystals begin to form, stabilized by the partially solidified fat structure. The blades continue to whip the mixture while keeping the internal temperature around 5 to 7 degrees Celsius, cold enough to form a spoonable texture without fully hardening. At this stage, inclusions like chocolate chips, cookie dough, brownies, caramel swirls, or fruit pieces are introduced. These mix-ins are added using ingredient feeders synchronized with the freezer output. The feeders are auger-based or belt-driven and feed precise quantities of inclusions into the flow stream so that distribution is even but gentle, ensuring that delicate ingredients are not crushed or smeared. As the frozen mix exits the freezer, it is immediately deposited into containers. Bluebell typically uses round paperboard cartons with plastic-coated interiors for ice cream, ranging from pints to half gallons. These cartons are automatically erected from flat stock, positioned on a conveyor belt, and filled via time pressure or piston-based filling heads. The heads are height adjustable and retract as the filling occurs to prevent air pockets or overflow. For varieties with variegates like fudge or fruit syrup, an additional stream is injected into the flow through a ribboning head, creating visible swirls as the carton fills from the bottom up. After filling, a lid is automatically pressed onto the container using pneumatic arms. The sealed containers pass through a rotary or linear check weigher that confirms the net weight is within spec. Underweight or overweight cartons are automatically rejected and sent to a separate path for inspection or rework. Accurate filling is essential not just for consumer expectation, but to ensure uniform freezing in the next step. The sealed containers are then conveyed into a hardening tunnel, which is essentially a long blast freezer where temperatures drop to 30 to 40 degrees Celsius. Inside, high-velocity fans circulate sub-zero air around the cartons, freezing the remaining liquid phase rapidly and reducing the core temperature of the ice cream to below 18 degrees Celsius. This fast hardening process is vital to preserving the fine ice crystal structure created during freezing. The air jets are angled and modulated to provide even exposure and prevent frost buildup or warping of the cartons. The hardened ice cream containers exit the tunnel and move into the packaging area, where they are inkjet printed with date codes, flavor identifiers, and batch numbers. These markings allow full traceability from raw ingredient to final sale. Cartons are grouped into multi-packs using collators and tray packers, then boxed by robotic case packers into corrugated shipping cases. Each case is sealed with tape or hot glue, scanned for correct labeling, and palletized using robotic arms. Pallets are stacked in specific configurations that maximize airflow for cold storage and are wrapped in stretch film to protect against moisture and dust. Finished pallets are transferred to a holding freezer, typically kept between 20 and 25 degrees Celsius, where product is stored until it's loaded into refrigerated trucks. These cold chain logistics are essential to prevent thawing and refreezing, which would cause ice crystal growth and negatively affect texture. Delivery schedules are timed to coordinate with storage capacity and retail demand, ensuring that the product reaches shelves still within the optimal quality window. Every point in the process is monitored through industrial control systems. Pressure sensors, flow meters, thermocouples, and programmable controllers gather real-time data on mix temperatures, freezer speeds, air injection rates, filling volumes, tunnel temperatures, and even ingredient feed rates. This data is reviewed both in real time and after production to analyze batch quality, identify issues, and implement continuous improvement measures. Any batch that deviates from target parameters can be traced back through digital batch logs and ingredient tracking systems, allowing for full quality control. In terms of sanitation, the Bluebell factory uses CIP, clean-in-place, systems on all tanks, lines, and freezers. After each production cycle, a sequence of hot water rinses, alkaline cleaners, acid washes, and final sanitizers is circulated through the system at high velocity. The cycle times, temperatures, and chemical concentrations are controlled automatically, and post-cleaning validations are performed using ATP swabs or microbiological plate tests to verify the absence of residue or bacterial growth. Mix-in feeders and surface equipment are cleaned manually between batches, especially when allergens or strong flavorants are involved. The result of all these carefully engineered steps is a product with uniform texture, balanced aeration, clean flavor release, and reliable scoopability straight from the freezer. Whether producing vanilla, cookies and cream, or limited edition seasonal flavors, the factory process remains consistent. Transform a raw dairy mix into a frozen dessert that maintains its integrity from the first pour to the final bite. Ben & Jerry's ice cream begins its journey inside large stainless steel mixing vats where fresh cream, condensed skim milk, and liquid sugars are combined in tightly controlled quantities based on batch-specific recipes, with all ingredients pumped from chilled storage tanks through sanitary stainless steel lines that use flow meters and valve junction boxes to direct each liquid into the blending vessel in the correct sequence, ensuring homogeneity without introducing unwanted turbulence that might destabilize the emulsion forming at the early stages of mixture development. The mixing vats are equipped with high-torque agitators and slow-speed sweep arms that rotate along the inside surfaces of the tank walls, scraping the mixture and pulling ingredients from the periphery into the bulk flow, preventing solids like stabilizers or milk powders from clumping or settling during agitation. While shear heads built into the agitator columns create localized high-energy mixing zones that dissolve particles evenly and allow for a uniform dispersion of all dry and liquid components. Once all base ingredients are integrated, including emulsifiers that help bind the fat and water phases and stabilizers that give the frozen product its structural resilience and slow down melting during consumption, the liquid base is pumped through a plate heat exchanger that rapidly raises the temperature to approximately 82 to 85 degrees Celsius in order to pasteurize the product, which not only destroys pathogenic bacteria, but also activates certain proteins in the milk that contribute to a richer, denser mouthfeel when frozen. After this high-temperature short-time treatment, the base flows immediately into a second section of the heat exchanger, where it is chilled using a closed-loop glycol or ammonia refrigeration circuit that drops the temperature back down to around 4 degrees Celsius in a matter of seconds. And the pasteurized, chilled base is then directed into jacketed aging tanks, which are maintained at low temperatures and fitted with slow, continuous agitators to prevent the separation of fat from the aqueous phase and to allow the stabilizers and emulsifiers to fully hydrate over the course of at least 4 to 8 hours. This aging step is crucial in Ben & Jerry's production process because it prepares the mix to accept not only high levels of air during freezing, but also unusually large and dense inclusions such as brownies, cookie dough chunks, peanut butter swirls, and toffee pieces that would otherwise sink or damage the structure of a weaker base. The aged mix becomes a foundation that can support extreme texture variation without phase separation or flavor loss. Once the aging process is complete, the base is pumped into continuous freezers that serve as the mechanical heart of the frozen transformation. And here, the mix is cooled down to roughly 5 to 7 degrees Celsius while being whipped rapidly inside a horizontal freezing cylinder, where rotating stainless steel blades scrape frozen mix from the walls and simultaneously fold in filtered air through precision-controlled injection valves that regulate the overrun, which is kept deliberately low, around 20 to 30%, compared to typical supermarket ice cream, in order to preserve the ultra-dense, ultra-creamy signature texture that defines Ben & Jerry's. The low overrun means that each scoop contains more ice cream by weight and less air, which makes the freezing process even more critical because dense product holds and transfers thermal energy differently than aerated product. And the refrigeration system must respond in real time to flow rate changes, viscosity spikes due to mix-ins, and fluctuations in pump back pressure, all of which can affect the crystal size and final structure of the ice cream. At this point in the process, flavors and inclusions are introduced using multi-head ingredient feeders, which are synchronized with the flow of frozen base to meter out solid components like brownies, peanut butter cups, or cookie swirls at a controlled rate, using screw conveyors or belt-driven chutes to deliver exact portions into the stream without breaking or over-mixing the inclusions. The goal is to allow each piece to be suspended in the flow with minimal shearing or melting, preserving chunk integrity and creating the variety of texture that Ben & Jerry's is known for. For variegates like fudge ribbons or caramel swirls, the freezer's output is directed into a stream-splitting pipe system where the flow of base ice cream is divided and recombined with injected streams of liquid syrup using spiraled ribboning nozzles that introduce the syrup in twisting arcs, embedding them throughout the product without fully blending them in, and allowing distinct, bold streaks of flavor to appear visually and texturally when the final product is scooped or cut. The combined ice cream and mix-ins flow directly from the freezer head into automated filling stations, where pre-formed pint containers made of wax-lined paperboard or biodegradable composite are delivered via a conveyor, raised into position by a pneumatic lift, and filled from a piston dosing head that controls both the volume and height of the deposit to minimize air pockets while achieving consistent fill weights across thousands of pints per hour. And the filling process includes an overfill compensation stage where a small mound is left at the top to account for post-fill settling and shrinkage during hardening. Once filled, the pints move immediately to a lidding station where domed plastic lids are placed and pressed down using synchronized arms that index precisely with the conveyor's motion, ensuring a tight seal without deforming the container. And each lid is automatically printed with a batch code, timestamp, and flavor identifier using laser or thermal inkjet printers that connect to the plant's centralized batch tracking system, which records every data point from base formulation to final packaging for regulatory compliance and internal quality control. From here, the sealed pints enter a spiral hardening tunnel, which is a vertically stacked freezer that uses high-velocity, ultra-cold air blown at 30 to 40 degrees Celsius to extract heat quickly and reduce the core temperature of each pint to below 20 degrees Celsius within minutes. And this rapid hardening is necessary not just to finalize the freezing process, but also to lock in the structural suspension of inclusions and prevent large ice crystals from forming during storage. The airflow inside the hardening tunnel is controlled by a network of fans and directional baffles that ensure every container receives uniform exposure regardless of its position on the spiral belt. And exit temperature is verified using inline infrared thermometers or embedded probes that signal if any container is under-hardened and needs to be rerouted or rejected. After hardening, the pints are automatically collated into case packers that group them into cardboard boxes or cartons, often 6 or 12 per case, and these cartons are sealed with either tape or hot glue before being labeled with shipping codes and scanned by barcode readers that confirm destination, flavor mix, and inventory count before the cases are stacked by robotic palletizers that arrange cartons into pallet configurations optimized for freezer airflow and shipping stability. Each pallet is stretch wrapped with cold-safe film, labeled with a master batch and product manifest, and transferred into deep storage freezers that maintain ambient temperatures between 25 and 30 degrees Celsius to prevent even microscopic temperature fluctuations that could cause texture degradation, especially for pints containing swirl-based variegates that are sensitive to heat migration and sugar inversion if stored improperly. Throughout the factory, process control systems monitor every mechanical and thermal parameter, from ingredient metering to packaging fill rate, using SCADA software that aggregates live data from flow meters, temperature probes, mixer speed controllers, and inclusion dispensers. And this information is used both for real-time error detection and long-term quality analysis that allows production managers to fine-tune the sequence of operations and ingredient preparation for future batches. Every component that touches the product is cleaned using CIP, clean-in-place systems that route caustic and acidic cleaning solutions through closed-loop pipes, tanks, freezers, and depositors, followed by hot water rinses and sanitizer cycles that are validated through swab tests and chemical residue sensors. And lines are completely stripped and reassembled during allergen changeovers or seasonal flavor transitions to prevent cross-contamination. Ben & Jerry's factory process is designed not just to produce a high-quality ice cream, but to do so with a level of texture complexity and inclusion density that requires more robust mechanics than standard ice cream production. From the strength of pumps used to move mix with dense brownie pieces, to the tolerance of nozzles that must deposit syrup without clogging or over-mixing. Each component is selected and calibrated to handle the brand's commitment to chunky, swirly, intensely flavored ice cream with integrity and repeatability. Tim Hortons donut production begins with a dry mix formulation containing enriched wheat flour, sugar, dextrose, non-fat dry milk, salt, leavening agents like sodium acid pyrophosphate and baking soda, and dough conditioners. These dry ingredients are stored in silos or large bagged quantities and conveyed into industrial mixers via auger-fed hoppers. Water, maintained at a controlled temperature between 26-30 degrees C, is added automatically by volume through solenoid-controlled valves. The mixture undergoes a high-capacity mixing process using horizontal paddle mixers that operate for approximately 10 to 12 minutes until a smooth, elastic dough forms. Dough temperature is precisely maintained to ensure consistent gluten development. The mixed dough is transferred to a resting conveyor where it undergoes a short fermentation stage, typically lasting 10 to 15 minutes. During this period, gluten strands relax, allowing easier downstream sheeting and cutting. The dough enters a sheeting system composed of heavy-duty rollers that gradually flatten the dough to a uniform thickness, often between 8 to 12 millimeters depending on the donut type. A dusting system coats the sheet with a thin layer of flour or starch to prevent sticking. Next, rotary cutters mounted on a continuous belt use oscillating blades and die shapes to stamp out ring donuts, filled donut bases, and specialty shapes. Hole cutouts are collected via vacuum suction and reintroduced into the dough stream to reduce waste. The shaped pieces drop onto a mesh conveyor belt, which transfers them into a proofing chamber. The proofer is a humidity and temperature-controlled enclosure typically maintained at 38-42 degrees and 75-85% relative humidity. Here, yeast-leavened donuts undergo final fermentation for 35 to 50 minutes, doubling in size. Upon exiting the proofer, donuts enter a continuous fryer via an infeed belt that gently lowers each piece into the oil. The fryer is filled with high-stability vegetable shortening, held at a consistent temperature of 185-190 degrees C. Conveyor arms with paddles submerge the donuts briefly before, Flipping mechanisms rotate them halfway through the cycle to ensure even cooking on both sides. Each donut spends 120 seconds in the fryer. Oil filtration systems continuously circulate and clean the oil through mechanical filters and carbon filtration media to maintain clarity and extend oil life. Excess oil is removed from the surface by air knives as donuts exit the fryer. Fried donuts transfer to a cooling conveyor, where forced ambient air reduces product temperature before glazing or filling. For ring donuts, a waterfall-style glazing system coats the tops with sugar glaze. The glazing machine contains a recirculating pump that delivers a steady curtain of glaze to ensure uniform coverage. Filled varieties proceed to an injection station. A synchronized multi-nozzle injector aligns with each donut and dispenses a precise volume of filling, such as fruit jam, Bavarian cream, or chocolate, into the center of the pastry using piston-driven pumps. Fill volumes are regulated down to the gram for product consistency. Specialty donuts requiring additional coatings, such as powdered sugar or cinnamon sugar, enter a rotating tumbler. The tumbler's perforated drum allows excess sugar to fall through while evenly applying the coating as the donuts rotate inside. Sensors monitor rotation speed and coating application rate. For chocolate or icing-topped varieties, donuts pass through a curtain enrobing system or a top-down depositor. The enrobing system consists of a tempering kettle and a heated pump that maintains the chocolate or icing at its working viscosity, typically around 40-45 degrees Celsius. Topping depth is controlled by belt speed and curtain thickness. Donuts requiring sprinkles or toppings are conveyed beneath a waterfall depositor or rotary sprinkler. The toppings are dispensed from a vibrating hopper that ensures even spread. Static charge may be applied in some systems to increase topping adhesion to the wet icing. Once decorated or filled, donuts proceed through a spiral cooling tower. The spiral conveyor allows a compact vertical footprint while offering extended cooling time, typically 15 to 20 minutes. Forced air circulation removes residual heat, allowing products to stabilize before packaging. Each donut then moves through a vision-based quality control system. High-speed cameras scan for defects in size, color, fill placement, or topping consistency. Items outside. Tolerants are rejected automatically using pneumatic pushers. Qualified donuts are then grouped by variety and type using a servo-controlled collation system. Products are aligned into lanes and counted by photoelectric sensors, preparing them for packaging. Packaging is handled by an automated tray loading system. Flat folded paperboard trays are erected using mechanical arms, and donuts are placed inside via pick-and-place robots with suction grippers. For assorted packs, robotic arms select donuts by type from buffer conveyors. Trays proceed to a lid applicator station, where pre-folded lids are pressed and sealed using glue jets or heat-sensitive adhesives. For retail cases, sealed trays are grouped and shrink-wrapped using polyolefin film, which is cut, wrapped, and heat-shrunk in a tunnel oven operating at around 160 degrees Celsius. Each finished pack receives an inkjet-printed date code and batch number from a variable data printer. The printer adjusts to the motion of the conveyor, ensuring clear marking without interrupting product flow. Packaged products are conveyed to palletizing stations. Robotic palletizers, equipped with vacuum or mechanical grippers, stack trays in precise layer patterns onto standard pallets. Slip sheets may be inserted between layers for stability. Full pallets are wrapped using a rotary arm stretch wrapper. The film roll is tensioned to apply a tight wrap without deforming the boxes. Wrapped pallets are transferred to refrigerated holding or shipping docks for distribution. Throughout the process, programmable logic controllers synchronize machine timing, belt speeds, pump volumes, and thermal settings. Human-machine interface panels monitor all parameters and log production data. The entire line is modular and scalable, allowing simultaneous production of multiple donut types. Conveyors interlink each station, minimizing manual transfer and optimizing flow. Changes in donut type or size are handled through automated tool change, systems, or quick swap components. Pre-programmed recipes stored in the central control system reconfigure the line settings within minutes. Staging silos and ingredient feeders are equipped with load cells to precisely meter dry ingredients. Liquid ingredients are stored in jacketed stainless steel tanks with inline agitators to prevent settling or stratification. The dry and liquid ingredient streams merge at the mixer's inlet via butterfly valves controlled by digital weigh scales. The dosing accuracy ensures batch-to-batch uniformity, critical for dough performance during proofing and frying. Proofing chambers are equipped with belt elevation systems that loop the dough pieces through multiple horizontal levels. Fans and humidifiers ensure even air distribution, and digital probes record temperature and humidity in real time. Fryers are segmented into temperature zones with independent heating coils managed by thermocouple feedback. This zoning ensures even coloring across all donut types, regardless of fill or topping. Oil levels are maintained by float-based control valves, and inline filtration runs continuously. Spent oil is periodically replaced using external storage tanks connected by insulated pipelines and pneumatic pumps. The icing station includes a recirculation tank and a filtration mesh that removes solid particles from reused icing. Viscosity is measured using a rotational viscometer integrated into the circulation loop. Decorative elements such as drizzle patterns or text are applied using programmable depositor heads, which trace patterns based on CAD instructions and synchronize with conveyor speed to ensure alignment. Filled donuts pass through an X-ray inspection tunnel, identifying underfilled or foreign material contaminated units. Rejected items are diverted to a side conveyor for manual review. Donuts for seasonal assortments are coded with quick response QR markers beneath their trays, allowing downstream distribution centers to sort mixed lots via machine vision systems and RFID tracking. Dunkin' Donuts. Donut production begins with dry ingredient blending, high protein wheat flour, dextrose, sugar, soy